Assalamualaikum and hello everyone. In this session, we're going to continue with eigenvalue and eigenvector. So in a previous session, we have looked on how we develop characteristic equation. Okay, so for 2 degrees of freedom, yeah. So first step is that you need to develop the equation of motion. So I'll write it as EOM, which is equation of motion. That's the first step that you need to do. And second step is that you need to divide this equation of motion with the mass itself. So for equation 1, you divide it with m1, and for equation 2, you divide with m2. And next, we change it into matrix form. So we get it in terms of this. And fourth step is that we need to assume harmonic motion. Why do we need to assume harmonic motion? So that x double dot 1 will become v1 and v2, and x1 and x2 will also become v1 and v2. And after that, we need to rearrange it. Yeah. So the fifth step is that we need to rearrange to become matrix A minus lambda. So lambda is actually omega squared. Yeah. A minus lambda identity matrix multiply with the V matrix equals to 0. So in a previous session, we have already developed our characteristic equation. So how do we get the eigenvalue and eigenvector from this characteristic equation for 2 degree of freedom system? So let's see for this problem. Okay, let's use some values so that we can get values of eigenvalue and eigenvector. So let's see if the example given is K1 equals to 20 Newton per meter. K2 is, let's assume, 10 Newton per meter. And mass 1 is given as 1 kilogram, and mass 2 is given as 1 kilogram. So after you develop your characteristic equation, so you need to put in all values given into the matrix. So since we already know the value of K1, K2, M1, so basically we're going to put into the matrix A. Okay. So now matrix A has become K1 is 20. So with K1 is 20 plus 10, and M1 is 1 kilogram. So this is 1. K2 is 10. K2 is 10. M2 is 1. K2 is 10. So it becomes 30, negative 10, 30, negative 10, negative 10, and 10. Minus lambda 1, 0, 0, 1. V1 and V2 equals to 0. Why equals to 0? Because this is a free vibration. So if you can see here, it's equals to 0. So it equals to 0. So if you learn about mathematics, we know that since our matrix V cannot be 0, so we can simplify it by saying that matrix A minus lambda I equals to 0. So basically, matrix A minus lambda I equals to 0. Okay? So what we're going to do now is that we're going to solve this using, this is what we call as Cramer's rule. Okay? So basically from here, it's actually we expand this. Okay, if you expand this, it becomes 30 minus lambda, negative 10, negative 10, and 10 lambda, multiply by V1, V2 equals to 0. So what I did was I multiply lambda into the identity matrix, and this is what I get. Yeah. So in order to solve this, we're going to use Cramer's rule. So what is Cramer's rule? Cramer's rules mean this, multiply this, minus this, multiply this. So 30 minus lambda, multiply by 10, sorry, this is 10 minus lambda. It's not 10 lambda, it should be 10 minus lambda. So 10 minus lambda, okay, minus, so this multiply by this, so negative 10 multiply with negative 10. Then this equals to 0. So what we do, we're going to expand this and so on. So the equation becomes 300 minus 30 lambda minus 10 lambda plus lambda squared minus 100 equals to 0. So next, we're going to rearrange whereby we will write higher order first. So what does it mean by higher order? Okay, so this is higher order. This is the second higher order, and this is the least higher order. So if we rearrange it and solve it, we'll get lambda squared minus 40 lambda plus 200. So how do we get the value of eigenvalue, which is the lambda itself? So we can use our calculator. Okay, so you can use your calculator, scientific calculator, to obtain the value of lambda. by using your calculator. So lambda 1 is 5.8579 and lambda 2 is given as 34.1421. So remember that when you use your calculator, you get two value of lambda, yeah, which is lambda 1 and lambda 2. Remember that lambda 1 needs to be smaller than lambda 2. Okay, so this is our eigenvalue. Okay, and in vibration, normally what we want to find is that we want to find the natural frequency, which is omega. So since lambda is equals to omega squared, therefore omega 1 squared is 5.8579. Okay, because omega squared is lambda. So omega 1, which is the natural frequency, is given as the square root of this. So you get 2.4203, and the unit is radian per second. And since omega 2 squared, which is lambda 2, is equals to 34.1421, so omega 2 is 5.8431 radian per second. Okay, so now we have obtained our eigenvalues and our natural frequency values. So next is that we want to obtain the eigenvector. So what is eigenvector? Eigenvector is the node shape. So again, we need to call back this matrix. Okay, we're going to use this matrix because in the end, what we want to do is that we want to find V1 and V2, right? So since we already know lambda, so we can find V1 and V2. So I write back that 30 minus lambda minus 10 minus 10, 10 minus lambda equals to multiply with V1 and V2 is equals to 0. So by using the first row, okay, this is the first row. For lambda, 1 equals to 5.8579. Okay, because we're going to have two mode shape or eigenvector, which is eigenvector 1 and eigenvector 2. In order to get eigenvector 1, we need to use lambda 1. And to get eigenvector 2, we need to use lambda 2. So for first eigenvector, which is lambda 1, okay, if you use the first row, 30 minus lambda 1 V1, okay, this multiplied by this, minus 10, which is this, multiplied by V2, is equals to 0. So since we already know our value of lambda 1, just this one, just replace it in the equation. We get 30 minus 5.8579 is equals to 10 V2. So V2 is 2.4142. So you must be curious, what is the value of V1? Yeah. So in vibration, when we have mode shape, let's say V1 and V2 or eigenvector, we normally normalize V1 to be close to 1 so that it's easier for us to determine V2. So the first mode shape, which is the eigenvector 1, is given as 1, which is V1 because you normalize it, okay, and V2 as 2.4142. Okay, 2.4142. So this is how we obtain eigenvector 1. So to obtain eigenvector 2, I mentioned that we need to use the second eigenvalue. So for lambda 2 equals to 34.1421. So we can use the same, we can use the first row. Okay, so 30 minus lambda multiplied by V1, which we will normalize it as 1 later on. Okay, minus 10 V2 equals to 0. So since we know the value of lambda 2, which is 34.142, so this equation will become 30 minus 34.1421 multiplied by 1, which is the value of V1, equals to 10 V2. So V2 is negative 0.4142. So the eigenvector 2 is 1, which is value of V1, and the second one is our V2, which is negative 0.4142. Right. So how to represent this graphically? All right. So since all of these are in positive value, okay. So let's say this is 0. First, we have positive 1. And second is 2.41. Okay. So this is the location of our V1. And this is the location of our V2. So when we want to draw a graph, we can draw it like this. And it goes down. So this is actually your V1 and V2. Right, so this is the representation for eigenvector 1. And for eigenvector 2, since we have positive and negative value, so let's say this is 1, and this is negative 0.4. So draw the first one first, which is V1, and second is V2. So we'll start from 0 and then connect it to this one, which is a V2, and goes up again. So this is our V1 and this is our V2. All right, so that's all for this session. In the next session, we're going to look on how we're going to develop or how are we going to obtain eigenvalue and eigenvector for 3 degree of freedom problems. Thank you very much. See you again.